Thanks for your introduction. Hi, everyone. My name is Patrick Perea, and I work at the University of Grenoble in France. And in this presentation, I will talk about navigation and guidance in augmented reality. Okay, so this is what a user looks like when trying to look for digital objects in his environment. He has no guidance information on screen and no knowledge about the off-screen environment. Because of the restricted field of view of the camera, he has to turn around the spot to explore his environment. And if we include guidance information on screen, it must be on the edges of the screen, because the center is used to access this digital information that we call the points of interest. And finally, there may be a lot of off-screen objects that corresponds to the user interest. So to make a proper guidance system in augmented reality, we have two requirements. First, the guidance system should not be intrusive on screen. And secondly, the guidance system should be able to manage dense environments. So our final question is how to visualize off-screen objects in augmented reality without overloading the user interface. There are many techniques that have been developed to show the location of off-screen objects. We are going to detail some of them here. Obviously, we have the arrows. So the arrows are often used to show location, to show directions to off-screen locations. However, they have never been tested in dense environments. Secondly, we have the halo. So the halo is a technique that shows the location and distance of off-screen objects using circles. So how does it work? We simply draw a circle here, whose center will be the off-screen object, and the radius is the distance between the off-screen object and the edge of the screen. So what the user sees on screen is just an arc. And this arc is enough for him to mentally complete the figure and understand where is the point of interest and how far is the point of interest. So the bigger the circle, the further the point of interest. The problem is that when you have many, many objects around you, it leads to many overlaps on screen, which really decreases the readability of the user interface. So to resolve this issue, the wedge technique has been introduced, and it uses triangles instead of circles. Again, the problem is that when you increase the number of points of interest up to 30, well, the wedge system is not robust enough to prevent the overlapping problem to occur. And in augmented reality, we have the AroundPlot. The AroundPlot is a technique that works in 360 degrees. So we display small points on the edges of the screen to show the location of off-screen objects. The main benefit here is that it considers all the directions around you. But the problem is that when you have many objects, it leads to a dense cloud of points in a small section of the screen, which decreases the readability of the user interface. If I summarize the related work so far, we get this table. So on the columns, you have all the techniques. On the lines, we have the requirements needed to make a proper guidance system. As you can see, none of the technique is perfect. None of the techniques fully satisfies all the requirements. So to satisfy the requirements, we introduced Halo 3D as a technique that works in augmented reality, that deals with the dense environments, and that is not intrusive on screen. So how does it work? It's simply an adaptation of the halo in augmented reality. So we project 3D point of interest on the device screen's plane, and we apply the same algorithm as the classic halo. And then to avoid the overlapping problem, we simply aggregate the circles when they visually overlap on screen. So we take the centroids of the projections of the point of interest, and we draw a circle whose center will be this centroid. And this circle replaces the overlapping circles, of course. So now the purpose, and it goes like this, yeah. So here we have the animation in real time. So now the purpose of our first user study is to compare Halo 3D with the AroundPlot, because this is the only technique that has been tested in dense environments and in augmented reality. And also to compare Halo 3 with the arrows, because they are widely used in today's navigation systems. So we compare the three techniques, and the objective here of the task was to find an off-screen object placed around users. So the target was designated by the green color, and we ask user to search for this target and select it to validate the task. Okay, so we tested two densities of environments, a low density with 5 points of interest and a high density with 50 points of interest, and two movement amplitudes, a narrow movement inferior to 80 degrees and a large movement superior to 120 degrees. So a large movement is basically to reach a point of interest placed behind you. For each technique, users perform 6 iterations for both environment and amplitude conditions. So it's basically 24 pointing tasks for each technique and 72 pointing tasks for the whole experimental task. At the end of the session, we conclude the session with an interview to collect users' feedback. And we obviously measure the time to complete the task. However, we did not find a strong effect of the density environments on the task completion time, and we did not find a strong effect of the techniques on the task completion time. However, here what you can see is the task completion time for all the techniques and for both type of movements. We observed that users spent a bit more time using the AroundPlot, here in red, than the other techniques. And actually, the task completion time is made of 2 steps. The first one is the visualization interpretation time, which is the time needed to look at the visualization and understand which direction has to be followed. And then the second step is the off-screen guidance time, which is the time needed to bring back the off-screen point of interest back on your field of view. So if we look at the first step here, you can see that statistically, users spend significantly more time trying to interpret the AroundPlot interface than the other techniques. And there are not so much time differences between the arrows and the halo. And this is due to the fact that the AroundPlot displays small points on screen. So it's much more harder and difficult to spot the green one, which is the target, compared to spotting a green arrow or a green circle on screen. And if we look at the second step, the off-screen guidance time, there is not so much time differences between the techniques. So this means that the task completion times is hugely influenced by the visualization interpretation time. What can we conclude from this first user study? First, Halo 3D has similar time performances as the arrows, while being less intrusive on screen. And secondly, the arrows is faster. The Halo 3 is faster than the AroundPlot. However, from the conductor interview at the end of the session, users raised concerns about the way the aggregation was visualized on screen. Because Halo 3 only indicates the direction, yes, towards the centroid of a cluster. So we lose the information about the spatial distribution of the point of interest inside of a cluster. So from our first 2 requirements at the beginning of the presentation to make a proper guidance system, we decided to include a 3rd requirement, which is the spatial distribution. The ability to show how the point of interest are spatially distributed inside of a cluster. To satisfy this requirement, we say, hey, why don't we modify the way the aggregation is visualized on screen? And we came up with 2 new techniques. The first one is based on the idea that small overlaps between the circles will not disturb the user. So we authorize small overlaps between the circles to avoid too much aggregation and be able to understand how the point of interest are spatially distributed. And it goes like this. So if I pause the video here, you will see one overlap, which means that we avoid too much aggregation, and you can understand how the point of interest are spatially distributed here. The second technique is based on curves. So the idea here is to display curves instead of circles for the aggregation to be able to understand the visual extent of the clusters. And it goes like this. So now the purpose of our second user study is to compare these 2 new techniques with the 3 previous techniques we compared in the first user study. Here the objective was to find 35 points of interest placed on one face of a machine. So to reproduce complex industrial environments, we took a picture of a real production machine and we printed this picture on a 3 meters per 75 centimeters large panel. The task was subdivided into 2 subtasks. The first one was a locate task. Here the objective for the user was to estimate and guess the location of the off-screen point of interest only by looking at the visualization on screen. So we presented on the computer a grid, and we asked users to click on the cells in which they thought one or more points of interest were located, here in red. The second subtask was an exploration task. So here the objective was to find and search and find one by one all the points of interest on the machine in the order that I wanted. For this experiment, users performed the training phase and immediately performed the experimental task for each technique. So we asked users to perform the locate task and then the exploration task. And when there were only 10 points of interest left on the machine, we asked users to perform again this process. So again the locate task, again the exploration task, just to allow us to study which technique better improves the understanding of the off-screen environment in cases of high-density environments, in cases of low-density environments. We conclude the session with an interview to collect users' feedback, and we measure the time to complete the task as well as the number of incorrect answers on the grid. However, we did not find strong effect of the techniques on the exploration time and on the number of incorrect answers, but we collected strong qualitative feedback in this user study. So we took the overall feedback given during the experiment, as well as the answer in the questionnaires, to create this table. So you can see here on the columns the technique we've tested, and on the lines the 3 requirements needed to make a proper guidance system in augmented reality. As you can see, none of the techniques is perfect. However, I want to get back on 3 details here. The first one is that there is a problem with the curves when all the points of interest are distributed around you, because it leads to a single curve that goes from one side of the screen to the other. So you end up with a visualization that does not provide any useful information about the off-screen environment. Just like 30 arrows on screen, you'll be useless. We have kind of the same problem with Halo 3D Star because it leads to many overlaps on screen which were judged as visually disturbing by users. And finally, users felt more comfortable using the Halo 3D Stars compared to the curves, simply because with Halo 3D Star you can see the complete arc here on screen. So it's mentally easier to complete the figure and understand where is the point of interest. But with the curves, you never see the complete arc on screen, so it's mentally more difficult to complete the figure and understand where is the point of interest. So what can we conclude from this user study? First, all Halo-based techniques have similar performances, but Halo 3D Star and the curves were judged as more able to show and display the spatial distribution of the point of interest. So in this presentation, I presented 3 variations of Halo techniques that works in augmented reality. We saw that Halo 3D had similar time performances as the arrows, while being less intrusive on screen, and is faster than the AroundPlot. And secondly, we saw that all Halo-based techniques have similar performances, but the curves and Halo 3D Stars were judged more able to show the spatial distribution of the point of interest. As none of the techniques is perfect, future work will focus on making a technique that automatically adapts to his environment, like a hybrid technique. And this concludes my presentation. Thanks a lot for your attention, and I will be glad to answer any question.
Questions?
Hello, Laurence from LMU Munich. My question was, how works the projection when a point is exactly on the back of the user because the projection arrived, in theory, on the screen? So how do you indicate the user virtual object is really behind the user?
Well, actually, you can't, from the visualization, you can't know if the point of interest is behind or in front. The only way to understand if the point of interest is behind is by moving yourself and follow the direction of the circle, for example. So as you move, your circle will be smaller and smaller, and you will reach the point of interest progressively to which is behind. So the only way to understand where is the point of interest, if it's behind, is by moving dynamically, not statically.
Questions? Yes. And then another question there. All right. Go ahead. Please.
Thank you. There were some trainings. You had some trainings, the 3 Halo and Arrow one. You trained the users, yeah?
Speak louder, please.
You trained users before using Arrow ones and Halo ones. So did you consider random training, or first you trained them Halo, second you trained them Arrow ones?
For which user study? Anyone?
Anyone, in the training ones.
Well, no, in the second user study, users perform the training phase for one technique and then immediately perform the experimental task for this technique. Okay? So, for example, if they started with Halo, they will train with the Halo and then immediately perform the experimental for this Halo. And then they will switch the arrows, train for the arrows, and perform the experiment for the arrows. Okay, so this is the second user study. And the first one, we randomized the way which technique will be tested, in which order.
Won't it affect the way that they perform, the speed of doing it? Because, you know, when they do the third learning, they are adapted to the way that they should do it. I mean, maybe random learning will be better. For example, first Halo for the first user. I don't know, for the second user, Arrow ones could be the first one.
Yeah?
I think that could be the better training. Did you get what I mean?
No.
So why didn't you randomize the training on the second user study? That's what she's asking.
If I do random...
Why did you not randomize the training?
In the second user study?
Yes.
Because there were too many techniques. There were 5 techniques in the second user study. So the problem to make all to test all the techniques in the same training session and to do the random order is that if you started by testing, for example, the Halo, then you test the Halo, then you will testing the arrows, you will testing all the techniques in the same training session, and then we will perform the experiment for one technique. So maybe you thought that you'll be forgetting what you learned in the training phase because there were too many techniques. So that's why we did one technique, and for this technique, training and then experiment, and not random. I'm not sure.
You can take it offline. Well,
hi, Tim Dwyer, Monash University. I was just wondering, in your points of interest all had uniform kind of importance or priority. I wonder if how would you extend your techniques if you needed to show different levels of priority associated with those points of interest?
Okay, so here in this case, we consider that all the points of interest have the same level. Okay, the thing is that in the industrial application, before showing the point of interest on your screen, you first perform a filtering phase. Okay, so you select the point of interest you're interested. For example, if you are in an industrial environment, you will select the point of interest that are high priority one. For example, errors on the machine, alerts, something like that. You will be filtering all these points of interest, and you will be showing only the point of interest for this priority. So at any time right now, we are showing the same levels of priority for one for this point of interest. The thing is that we can't. We thought about showing various types of priorities in the same user interface. So we thought by showing, for example, distinguishing the levels of priority using the colors, for example. Okay. The thing is that we thought that the colors will be too much visually disturbing for users because, for example, with the circle, you have the radius of the circle. You have to understand the shape of the circle. And then there is the aggregation. So there are 3 things. and then you add the color for distinguish the types of priority, the types of priority of point of interest. So I think it's too many things for a user, for a system that only will be using from time to time.